Good morning, everyone. I'm Eklavya Sharma. I'm a PhD student at IAC, advised by Professor Jugal Garg, and today I'm going to talk about fair division. Okay, let's talk about the fair division of goods. Okay, so in this problem, we are given a lot of goods and we need to divide them among n people. All the people are equally deserving, so we don't want to give too many items to one person and too little to someone else because that would be discriminatory. So this is what I mean by fairly dividing the goods among the people. Okay. There are two versions of this problem. There's a divisible version, also called the continuous version, where we're allowed to cut up the items into pieces and then give different pieces to give different people. And there's an indivisible version, also called a discrete version, where we're not allowed to cut up items into pieces. So when items are divisible and homogeneous, then the problem is trivial. Let's say I want to divide fruit juice fairly among n people. So I'll just measure out n equal parts by volume, and that would be a fair division. Okay. The problem becomes more interesting when the goods are divisible, when the goods are either indivisible or the goods are heterogeneous. For example, if we have a cake in which some part of it is chocolate, some part is strawberry, and some part has more icing, some part has less icing, and different people have different preferences for different regions of the cake, then the problem becomes more interesting. Okay. Now, this problem has many applications. Okay. And the application which is the most important to me was fair division of toys and candies. When in my childhood, whenever our parents would get stuff for me and my sister, then fair division would ensue. And if our parents did not divide the items fairly among us, then we would accuse them of favoritism and all. Okay. So if some of you are planning to have multiple children in the future and you don't want to suffer like my parents, then you should pay attention in this talk. Okay, there are also a few more serious applications like dividing inheritance, business partnership dissolution, and divorce settlements. Okay. For the case of divisible goods, we have applications like dividing land, dividing radio frequency spectrum among communications companies, and dividing airplane runway time among airlines. So let's formalize the problem. Formalizing means that we are going to decide the input and output format of the problem. Okay. So we are given a set capital N of agents, and we assume that the agents are numbered from 1 to n. Okay. And agents can be either people or companies or countries, whatever it is. We're dividing goods among agents, and these agents can be any of these things. Okay. We are given a set capital M of goods. In the divisible setting, we can assume without loss of generality that the set M is a unit interval on the real line. Okay. When in the indivisible setting, we can assume that capital M is the set of M goods numbered from 1 to n. Each agent I has a valuation function associated with her. Okay. This function takes as input a subset of the goods, and it outputs a non-negative real number that tells us how much they like that set of goods. So the input to our problem will be a set of n valuation functions, one for each agent. We have a few reasonable assumptions on the valuation functions. The first is that the valuation of the empty set is 0. And the second assumption is called monotonicity, which means that if S is a subset of T, then the value of S is at most equal to the value of T. Sometimes we also assume that valuations are additive. Okay, this means that if we have two disjoint sets S and T, then the value of S union T is equal to the value of S plus the value of T. In this talk, I'll assume that all valuations are additive except if I explicitly say so otherwise. Okay. Now, additive valuations are very common in practice, but there are some exceptional cases where valuations are not additive. For example, the value of a pair of socks is a lot more than twice the value of an individual sock. That's because a pair of socks is useful because you can wear them. An individual sock is pretty much useless. Okay? And we also have the opposite scenario, that if we have two identical cars and let's say you're not allowed to sell them, rent them, or share them, then two cars is not going to give you a lot more value than one car, because at any given point of time you can only drive one car. Getting an additional car isn't really going to be as beneficial as having one car. Okay. For indivisible goods, additivity means that the value of a set of goods is equal to the sum of the values of the goods in that set. Okay. So when we have indivisible goods and the valuations are additive, then we assume that our input is given by a matrix where the entry in the ith row and the jth column is the value of the jth good for the ith agent. The output of our algorithm the output of fair division is an allocation. An allocation basically tells us which goods to give to which agent. Okay. So we formalize this as an n tuple. So it's a sequence that has n entries, and each entry is a set of goods. And all of these sets are disjoint, and their union is equal to the entire set of goods. Okay. And the ith entry in this tuple, which we denote by xi, is called agent i's bundle. So this is the set of goods that agent I will get. And okay, so now we're done with formalizing the problem pretty much, and now our task is to find an allocation that is fair. So now let's look at definitions of what it could. Let's define what fairness means. Okay. So let's start with a notion of fairness called NV freeness. Okay, we say that in allocation X, in an allocation X, we say that agent I envies agent J if, according to agent I, J's bundle is more valuable than her own bundle. Okay, and we say that an allocation is NV free if no one envies anyone else. So here I have an example where we have three goods: a green candy, a cookie, and a lollipop, and we have two agents, Alice and Bob. And the value in the cells correspond to the valuations of the goods for the agents. Okay. So consider the allocation where Alice gets the green candy and the cookie, and Bob gets the lollipop. Then this is an NV free allocation. Why? Because Bob's value for his own bundle is 25 and his value for Alice's bundle is 20. So Bob does not envy Alice. Alice's value for her own bundle is 6 and her value for Bob's bundle is also 6. So Alice also does not envy Bob. Another notion of fairness is called proportionality. We say that an allocation X is proportional if for every agent I, the value of their own bundle is at least their value for the entire set of goods divided by n, where n is the number of agents. So let's look at the same example that we had in the last slide. So here, okay, so this value, which is the value of the entire set of goods divided by n, this is called the proportional share of an agent. So in this example, Bob's proportional share is 22.5 because there are two agents, and if we sum up the values of all the goods for Bob, then that comes out to be 45. Similarly, Alice's proportional share is 6, and we can see that in this allocation, each agent is getting at least as much as their proportional share. So this is a proportional allocation. Now, let's see how to divide a cake among two agents fairly. Okay. To do this, we'll use a technique called the cut and choose protocol. Okay. So let's say the agents are called Alice and Bob. So Alice cuts the cake into two pieces that have an equal value to her. Then Bob picks the piece which he prefers, and Alice gets the remaining piece. Now this allocation is NV free. Why? That's because Alice is cutting the cake into pieces of equal value. So whichever piece she gets, she she will not be envy free. I mean, she will not envy Bob. And Bob does not envy Alice because Bob chose the piece which he prefers. So he would not envy Alice. Okay. And this works even for non-additive valuations. So this shows us how to get an envy-free allocation, but what about a proportional allocation? But it turns out we don't need to worry about that because an envy-free allocation is also a proportional allocation when valuations are additive. So let's see, why is this? So the proof is like this. Pick any agent I, then agent I's value for his own bundle is at least his value for agent 1's bundle. And similarly, Vi of xi is greater than or equal to Vi of x2, and so on. We get these n inequalities, and when we add all of these inequalities together, we get that Vi of xi is greater than or equal to agent i's proportional share. And so we're done. Yeah, this shows that for every agent, and if x is an envy-free allocation, then x is also a proportional allocation. So the cut and choose protocol only works for 2 agents. Now let's see how to get a fair allocation when we have n agents, where n can be even more than 2. So we'll use the Dubin-Spanier algorithm, and this will give us a proportional allocation. So let's imagine that our set of goods is a one-dimensional interval. Okay, let's say that the set of goods is a cake. Now the algorithm is this, that for every agent I, we tell them to mark a point xi on the cake such that the value of the cake from a to xi is equal to their proportional share. Okay. Now once everyone has put a mark on the cake, then we pick the agent whose mark is the leftmost among all the marks. Okay. And then let that coordinate be xk. Okay. Then we give the piece from the left end to xk to agent k, and then we'll see later what to do with the rest of the cake. Okay. Now the key observation here is that agent k is getting his proportional share, so agent k is happy. But what about the other agents? According to the other agents, the piece that agent k got is less than or equal to their proportional share. That's because their marks on the cake are to the right of agent k's mark. Okay, and that means that the part of the cake that remains, the value of that is equal to n, is at least n minus 1 times their proportional share. Okay, now to divide the remaining cake among the remaining agents, we'll just recursively use the Dubin-Spanier algorithm. Okay, and we can show that this algorithm's output is proportional. And a good quality of the output of this algorithm is that each agent gets a contiguous piece of the cake. It's not like we're giving an agent some piece from one end, some piece from the other end, and so on. It's one contiguous piece. This is very useful in, let's say, fair division of land or radio frequency spectrum. So that was for proportional cake cutting, but what about envy-free cake cutting? Okay. So it has been proved that envy-free allocations always exist, and this is true even if we insist on connected pieces. But when there are more than 2 agents, the algorithms for this are very complicated and they have a very large running time. Okay. But for some special cases, we have efficient algorithms, like when the valuation functions are piecewise constant, then efficient algorithms exist to compute this using the Eisenberg-Gale convex program. So we looked at fair division of cake, but fairness is not the only concern. Okay, so let's look at an example where we have a cake for which half of the cake is chocolate and the other half is blueberry. Okay, and Alice prefers blueberry and Bob prefers chocolate. Okay, now here I've drawn 2 different ways of cutting the cake up into 2 pieces. On the left side, so both of these allocations are fair, but one of them is better. Why? Because in the second allocation, we're giving Bob all the chocolate and Alice all of the blueberry. So if we ask Alice which of these allocations she would prefer, she would pick the right one. And Bob would also pick the right one. Okay. So how do we formalize this idea? Okay. We do this using a concept called Pareto optimality. So intuitively, an allocation is Pareto optimal if it's impossible to make someone happier without making someone else sadder. Okay. So a bit more precisely, we say that an allocation X Pareto dominates allocation Y if and only if both of these conditions are true. The first condition is that no one prefers Y, which means that Vi of Xi is greater than or equal to Vi of Yi for all agents I. And the second condition is that someone prefers X, which means that there is an agent I such that Vi Xi is greater than Vi of Yi. So both of these conditions are almost the same, except that in the second one we have a strict inequality. And we say that an allocation X is Pareto optimal if it is not Pareto dominated by any other allocation. So Pareto optimality is a notion of efficiency, which means that if an allocation is Pareto optimal, then we say that it's efficient, otherwise it is inefficient. But it's a weak notion of efficiency, because sometimes there are scenarios where we can make someone a lot more happy by making someone else slightly sadder. Okay? So if you want, so there is a stronger notion of efficiency called Nash social welfare. Okay? So this is literally the average happiness of an allocation. By average, I mean the geometric mean. And an allocation that maximizes the Nash social welfare is called a Nash optimal allocation. Now, first of all, a Nash optimal allocation is also Pareto optimal. And that's because let's say we have a Nash optimal allocation that is not Pareto optimal, then it means that some other allocation Pareto dominates that allocation. But this Pareto dominator would have a larger Nash social welfare, and that would give us a contradiction. Okay, so that's the proof. Okay. But the good thing about Nash optimal allocations is not just that they are efficient, but often they are also fair. Okay? For example, in a Nash optimal cake division is envy free. Now this is not easy to prove, so I won't go with the proof here. So we've looked at how to get fair and efficient allocations for divisible goods. Now let's look at how to do this for indivisible goods. Indivisible case is more complicated because for divisible goods, envy freeness and proportionality can always be guaranteed, but that's not the case for indivisible goods. Okay? Let's say we have just a single good that needs to be divided among two people. Then whoever gets the good will be happy and the other person will not be happy. So it's not possible to be fair actually in the indivisible setting. So, but even though we can't be fair, we can still be approximately fair. Okay? So here I have I've shown two different allocations where we have 8 identical items and 3 agents. Okay. So here we can see that in the first allocations we are being a lot more unfair compared to the second allocation. Okay. So even though we can't use envy freeness and proportionality as our notions of fairness, maybe there are other notions of approximate fairness that we can still use and be approximately fair. So let's see what those notions should look like. To get some intuition, let's first look at an example. Let's say we have m identical goods and we have n agents. Okay, then each agent should get either floor of m by n goods or ceiling of m by n goods. Okay? Now, and this is the best that we can do. It's not possible to be any more fair than this. Okay, so how do we generalize this idea when the goods are not identical? Okay. So the key observation here is that if you look at any two bundles in this example, they differ by at most one good. Okay. So this is the observation we use to define a notion of fairness called EFX, which stands for envy free up to any good. In an allocation X, we say that an agent I strongly envies agent J if even after removing some good from agent J's bundle, agent I still envies agent J, which means that agent I still thinks that agent J's bundle is better even after removing that good. We say that an allocation is EFX if no one strongly envies anyone else. So let's look at this example, okay, where I have 4 goods, a lollipop, cookie, green candy and a donut, and we have 2 agents, Alice and Bob. Okay. Suppose I give the lollipop and the cookie to Alice and I give the green candy and the donut to Bob. Okay. Then Bob's value for his own bundle is 29, but his value for Alice's bundle is 28. So Bob does not envy Alice. But Alice's value for her own bundle is 8 and her value for Bob's bundle is 9. So Alice envies Bob, but Alice does not strongly envy Bob. And that's because if we remove any good from Bob's bundle, then Bob's bundle will have a value of at most 7 to Alice. Right, so this allocation here is an EFX allocation. Now, 2 natural questions arise: that do EFX allocations always exist, and can we efficiently compute EFX allocations? Okay. So in general, the answers to these questions are not known, but there are a few special cases for which we know the answer. Okay. So when there are only 2 agents, then an EFX allocation exists, and when all agents have the same valuation function, then also an EFX allocation exists. And these results are true even for non-additive valuations. For n equals 3, it was recently shown that an EFX allocation exists, and one of the authors of this paper is Professor Jugal Garg, who is my advisor, and another author is Bhaskar A. Chaudhary, who recently interviewed for a faculty position here. When there are 4 or more agents, then we don't know whether an EFX allocation exists or not, and this has been an open problem for a very long time. So because of this, people have looked into relaxations of EFX, which means that if we can't get EFX, then can we at least get something slightly worse than that? Okay, so people have looked at notions like EF1, alpha EFX, EFX with charity, and epistemic EFX. Epistemic EFX is a notion that I worked on, and recently I showed that epistemic EFX allocations always exist and can be efficiently computed, and we have submitted that result to IJCAI. So that was EFX. So EFX is a relaxation of envy freeness. Now let's look at a relaxation of proportionality. Okay. So let's go back to our example where we have 10 identical goods that need to be divided among 4 agents. Okay. Then every agent's proportional share is 2.5, but it's not possible to give everyone at least 2.5 items. Someone will get at most 2. Okay. So it's reasonable to assume that the expectation that an agent has should not be of 2.5 goods, should be of 2 goods. Okay. So that's the key idea here. So both proportionality and MMS are threshold-based notions of fairness, which means that there is a certain threshold and an agent is happy if their value for their own bundle meets that threshold or is greater than that threshold. Okay. So for proportionality, we use the value of the entire set of goods divided by n, but for MMS, we'll define the threshold differently. Okay. So MMS is for an agent I, their maximum share, which I'll denote by mu I, is the maximum value such that there is some allocation where every bundle has a value of at least mu I. Okay. So we can also write it in this other form. Okay. So let's define the score of an allocation as the value of the minimum valued bundle in that allocation. And then we define mu I to be the maximum score that we can possibly get out of any allocation. Okay. And since we have a max and a min here in this expression, that's why this notion of fairness is called max and min share. And we say that an allocation is MMS if every agent gets their maximum share. Okay. So again, we ask the same questions: do MMS allocations always exist, and can we efficiently compute MMS allocations? Okay. Now, again, for special cases, it's been known for a long time that when all agents have the same valuation function, then MMS allocations exist. And when there are only two agents, then also MMS allocations exist. But even here, even if we have two agents and both of them have the same valuation function, it's still NP hard to get an MMS allocation. So already we running into problems. And there is a known example with three agents for which an MMS allocation does not exist. So for this reason, people have started looking into relaxations of MMS. So if it's not possible to give everyone their maximum share, then can we at least give them some fraction of the maximum share? And in 2020, it was shown that there is an algorithm that gives every agent at least a 3/4 fraction of their maximum share. And this result was by Professor Jugal Garg and Setare Taki, who used to be a PhD student here at ISC. Okay, so that's it that I had to say. So let me just summarize this talk. We started by formalizing the fair division problem. Then for the case of divisible goods, we looked at envy freeness and proportionality. We saw how to get an envy-free allocation when there are only two agents using the cut and choose protocol. We then looked at the Dubin-Spanier algorithm to get a proportional allocation, and then we looked at what it means for an allocation to be efficient and two metrics for that: Pareto optimality and Nash social welfare. Okay. Then we looked at the case of indivisible good. We saw that envy freeness and proportionality need not always exist, and so we looked at two alternative notions of fairness called EFX and MMS. Now, fair division is actually just a tip of the iceberg. This is a big field called social choice theory. So this field is about how can multiple agents make a joint decision. Okay. So today, in today's talk, the joint decision was about how to divide goods among the agents. But we can also look at other kinds of decisions. For example, how to divide chores among the agents. Let's say a few people are living together and they need to divide the household chores among themselves, and we don't want to give too much work to one person. So that is called fair division of chores. Another problem is called splitting rent. Let's say two people move into an apartment and they're jointly paying rent, and it's a 2-bedroom apartment, but one bedroom is larger, has better lighting, better furniture, everything better. Now it would be unfair if both of them they split the rent evenly among themselves. I mean, obviously the person who's getting a better room should pay slightly more, but how much more? Okay. So these kind of questions are answered by the theory of fair rent division. Okay. Another question could be that, let's say a group of friends decide to hang out together and have fun on a weekend. So they have a lot of candidate activities. They could either go watch a movie, go to an amusement park, or they could play board games or whatever. Okay. So they have a lot of such activities, but they can't do all of them. They can only do some of them because they only have the weekend. Okay. So which activities should they pick? Now different friends will have different preferences and they want to come to a joint decision about what to do. So this again is a problem involving fairness and efficiency. Okay. Thank you. That's all I had to talk about. And in case you want to, let's say, try out fair division for yourself, I have these simple homework problems for you to do. Okay. So you can try out these problems right now or later, and you can just contact me if you want to discuss any of them.